In today's video, we solve the Ornstein-Uhlenbeck stochastic differential equation, the linear mean reversion model used in finance, statistics, and generative AI, and we land on this closed form. The SDE is this: dxt equals theta times mu minus xt dt plus sigma dwt. Theta is a positive constant, the speed of mean reversion. Mu is the long-run mean. Sigma is the volatility. The noise is additive. It does not scale with x. Look at the drift. When x sits above mu, the drift is negative. When x sits below mu, the drift is positive. So the process is pulled toward mu at rate theta. That is mean reversion. Because the equation is linear, we solve it with an integrating factor. Multiply through by e to the theta t. That factor is a function of time only. When we form yt equals e to the theta t times xt, Ito's product rule has no extra second-order term. This is not the Black-Scholes logarithm, where a nonlinear map on S produces the Ito correction. Set yt equal to e to the theta t times xt. Differentiate. dy equals theta e to the theta tx dt plus e to the theta t dx. There is no 1/2 second derivative piece. The integrating factor is deterministic. Now substitute dx, e to the theta t times mu minus x, dt, plus sigma dw. The two theta e to the theta t x dt terms cancel. What remains is dyt equals theta mu e to the theta t dt plus sigma e to the theta t dwt. Integrate from 0 to t. Yt minus y0 equals mu times e to the theta t minus 1 plus sigma times the integral of e to the theta s dws. Multiply through by e to the minus theta t and restore x. Xt equals x0 e to the minus theta t plus mu times 1 minus e to the minus theta t plus sigma times the integral from 0 to t of e to the minus theta times t minus s dws. The stochastic integral is a weighted history of the Wiener increments. Recent shocks count more. Old shocks are forgotten at rate theta. That is why the noise is not sigma wt. Take the expectation. The stochastic integral has mean 0. So the mean of xt is x0 e to the minus theta t plus mu times 1 minus e to the minus theta t. As t goes to infinity, the mean goes to mu. For the variance, use Ito's isometry. The variance of that stochastic integral is the ordinary integral of e to the minus 2 theta times t minus s ds. Change variables. Let u equal t minus s. The integral from 0 to t of e to the minus 2 theta u du equals 1 minus e to the minus 2 theta t over 2 theta. Carry out the integral. The variance of xt is sigma squared over 2 theta times 1 minus e to the minus 2 theta t. As t goes to infinity, that tends to sigma squared over 2 theta. That is the stationary variance. The process is Gaussian, so the long-run law is normal with mean mu and that variance. In finance, this is the Vasicek model for the short rate. In statistics, it is the standard mean-reverting noise. In generative AI, the same linear SDE appears as an Ornstein-Uhlenbeck noising process. The method is, write the linear SDE, multiply by the integrating factor, integrate, scale back. Then read the mean and the variance off the stochastic integral. I hope this derivation helped. This is QuantXYZ, quantitative methods for finance, statistics, and AI. Subscribe if you want the next one.